These sampling distributions.
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology, present the 2002 VA Epidemiology Summer Session.
Good day. My name's Gail Reiber. I'm the director of the VA Summer Epidemiology course. We're going to continue our course this morning in general biostatistics, and we're pleased to have as the faculty for this course Professor Marie Diener-West. Dr. West is a biostatistician at the Bloomberg School for Public Health, Johns Hopkins University. She'll review a little bit for us from the material we covered in the last session, and then she'll move on ahead with common statistical tests.
Thank you. Okay, so last time we had looked at only one group comparisons. Today what we'll be going to do is actually expand upon our discussion from last time, looking at hypothesis testing and confidence interval estimation for two group comparisons. What I'd like to do is review with you the example that we had covered last time by looking at this example and trying to interpret the output that we might get if we looked at a stata output. Now, most of you are probably not going to go back home and conduct research and make calculations by hand. At least I hope not. Most of you will probably go home and work with research teams or work with statisticians in which you might have the opportunity to interpret output from statistical analysis packages such as stata. And so although we went through the mechanics of constructing confidence intervals and performing hypothesis tests last time because it forms the basis for understanding where they come from, I'd like to show you the same example using stata today. One of the, and you don't need to know how to use this, I'm going to just show you how to interpret the output. And one of the nice features of stata actually is, if you remember last time, we had a sample of 25 infants and we were looking at their mean birth weight and the sample standard deviation that we had calculated. And in fact, we constructed a 95% confidence interval for the true mean birth weight of the population they were sampled from. We looked at a hypothesis test. Well, stata allows us to we don't need the data set. So I'm going to actually put in a command that says if I know the number of observations were 25 and the sample mean was 2,500 and the sample standard deviation in this data set was 900, how would I test a null hypothesis that the true population mean is 3,000? So I'd type in on this command line that I'm testing the null hypothesis of 3,000. And what I get, and I'm hoping that you can see this, I'll use the pointer to show, is that stata tells us, yes, you had 25 in the sample size. The sample mean was 2,500. The standard deviation was 900. So that means the standard error was S, the sample standard deviation, divided by the square root of the sample size. In other words, 900 divided by the square root of 25, which is 5, or 180. So remember that what we can do is take the sample mean of 2,500, add and subtract the appropriate t-value times the standard error to get a 95% confidence interval. So in fact, here's the 95% confidence interval. Can everyone see this? The range is from 2128 grams up to 2871 grams. And this now shows us a range of values that are consistent with the truth for the population mean birth weight based on the data that we observed. And it can be as low as 28 grams, as high as 2871. Now, remember the other way of making an inference is to inspect the confidence interval if we have a null hypothesis. So suppose the null hypothesis is that the true population mean birth weight was 3,000 grams. We'd look in that interval to see if it contains 3,000 grams. 3,000 is outside that interval. So based on inspection of the confidence interval, we'd reject the null hypothesis, conclude that based on our data, the mean birth weight of the population we sampled from appears to be something lower. than 3,000 grams. We could set up a null hypothesis that the true population mean is equal to 3,000. Stata doesn't know how to print Greek symbols, so this is the null hypothesis that mu equals 3,000 versus an alternative that the mean is not equal to 3,000. And Stata also doesn't know how to write not equals to, so it uses a tilde equals to. But it's 3,000 versus not 3,000. Here's the test statistic of negative 2.78. So does anybody remember from yesterday where that came from? I'll reiterate where it came from. The test statistic took the sample statistic, the mean weight of 2,500 grams, minus the hypothesized value of 3,000 divided by the standard error of 180. And if you go back and look at the notes from yesterday, that t statistic was negative 2.78. And if we looked up the p-value in the t-table, we would have seen that the p-value was about 0.01, 0.011. So in fact, what this is telling us that if we had set up a rejection region, remember that this is a fairly large sample size, so even without a t-table, the rejection region would have been t-statistics that were either greater than 1.96 or less than negative 1.96. This value is negative 2.78, which falls in the rejection region, so that would be one form of evidence for rejecting the null hypothesis. The p-value is also less than 0.05. So the conclusion that we get is that based on this p-value, which says there's only 1 out of 100 chance that we would have observed the sample mean of 2,500 if indeed the true population mean was 3,000. So is it likely or unlikely? Very unlikely. So we'd reject this hypothesis and conclude that the alternative, which says the true population mean is something other than 3,000, must be true. So by inspecting the confidence interval for 3,000, by looking at the result of the t-statistic falling in the far left tail of the rejection region, and by getting a very small p-value, all three would lead us to the same conclusion of rejecting this null hypothesis. Now, if we reached different conclusions based on those three methods, there must be something wrong. We should get the same conclusion with any of those methods. Okay, so any questions about what we just covered? Okay. Well, if there aren't, then what we'll do is go back to the our topic at hand right now, which is expanding this, just taking it to another level where our hypothesis testing and confidence interval estimation is going to be based on looking at differences between two groups, two independent populations, or we can also see that sometimes we might have pair match data in which we have before and after observations on the same individuals, pre versus post observations on the same individuals. So we'll see how we can use the same methodology that we've used for one group and expand it to two groups. So our interest, if we're dealing with a continuous outcome with two groups, is to either calculate a test statistic for the purpose of a hypothesis test, and here the null hypothesis is that the true difference in two population means is equal to 0. So here's where the term null hypothesis really arose. I had a question regarding this term as well. Last time we looked at just a one-group comparison. So our null hypothesis was just a hypothesis regarding the specific value of either the true population mean or the true population proportion. So we weren't interested necessarily in whether the true mean was equal to 0 or whether the true proportion was equal to 0. Usually we're interested in whether they take on some assumed value, either based on previous data or previous literature. But it truly is a null hypothesis when we're interested in comparing two groups. So for instance, if we have two treatment groups, treatment A and treatment B, we're often interested in knowing whether or not the two groups are the same. If the two groups were the same, then we would assume they were from populations where the true means were the same. So another way of saying that mu1 equals mu2, in other words, the two population means are the same, is to say that the difference between the two population means is equal to 0. So we'll be expanding hypothesis testing to this two-group comparison of means. We'll also look at calculating 95% confidence intervals for the true difference in population means. So with two groups, we're going to be setting up a test statistic in a very analogous way to the way we did for one group. If we have two means, we'll either use a z-test. We can use a z-test if we claim that we know the population variances or standard deviations in both groups. So if we know sigma 1, the population standard deviation from group 1, and sigma 2, the population standard deviation from group 2, we could use a z-test. Otherwise, if we don't know the true population variances, we would use a t-test instead of a z. So just like we did with a one-group comparison, most of the time we'll be interested in a t-test because we don't know the true population variances. We might need to make some assumptions about whether the spread or the variability in both populations are the same or equal or different or unequal. And we'll talk about that in a moment. So just as a review, in general, we said that the test statistic takes the form in the numerator of the sample statistic that we derive from our data minus the hypothesized value divided by the standard error of the sample statistic. So again, all that we need to know is what we have calculated or derived as the sample statistic. So that's the first part of the numerator, what the hypothesized value is, and also the standard error. So when we deal with a two-group comparison and we're setting up a null hypothesis that the difference in the true population means is 0, the hypothesized value is just 0. And the sample statistic of interest is the difference in our observed sample means. So let's look at this with an example from a very small clinical trial, just for illustration purposes. Suppose I had two independent groups of patients, 5 patients who were treated on drug, 5 patients who were treated on placebo, and these are continuous outcome measures that are looking at an anxiety score. So it's a drug that's aimed at reducing anxiety. And it was a randomized comparison of drug versus placebo. So we have these 5 measures on 5 separate individuals treated by drug and 5 separate individuals treated by placebo. And suppose then we calculated the means. So the mean anxiety score in the drug group was 16.8, and the mean anxiety score in the placebo group of 5 patients was 20.2. And suppose then we calculated also the standard deviations, 4.6 and 3.3 respectively in the drug and placebo groups. So where did these numbers come from? They came from using the formulas for mean and standard deviation based on those 5 observations in each group. And if we just looked at the difference in means, 16.8 minus 20.2 says that the mean anxiety score was actually 3.4 points lower on average in the drug group than in the placebo group. So does it look like the drug was effective in reducing anxiety? On the surface, right? So on the surface, it looks like it may have been effective. What we'd like to do is not just eyeball that difference. What we'd like to do is be able to look at whether this difference that we observe of 3.4 points is bigger than what we would have expected it to be just due to chance alone, even if there was no true difference in mean anxiety score between the two groups. So our test statistic is, again, we're going to set up a test statistic and base our decision making on this theoretical sampling distribution, where the test statistic of interest is the difference in the sample means minus the hypothesized value of 0, and then we'll divide by the standard error. This is a formula that we're not going to derive. You can take this as a given, that the standard error of the difference in means is based on 2 things. It's based on the variability that exists in the population as estimated by the sample. So in other words, it's partly determined by S1 squared and S2 squared, the sample variances, but the variability in those sample means, those possible sample means, is also influenced by the respective sample sizes in the drug and the placebo group. So here the sample sizes happen to be the same, 5 in each. We saw that the estimates of standard deviation were 4.6 in drug and 3.3 in the placebo. So if we go through the math, we would take that observed difference in means of negative 3.4, subtract 0, divide by the standard error, and we would get a test statistic of negative 1.34. So how do we make some sense of that? How do we go about making a statistical decision? Okay, so I'm hearing a couple of responses. One is we could calculate the confidence interval. We already have a test statistic, though, so we could make our statistical decision based on seeing whether this value of the test statistic falls in the rejection region, or equivalently, we could calculate a p-value, or equivalently, we could determine the 95% confidence interval and see whether that hypothesized value of 0 falls in the interval. So we'll do all three of those. So here is the rejection region that we would set up if we looked at the total degrees of freedom. Now remember, we have two groups now. If we looked at each group separately, the degrees of freedom for one group, because of the uncertainty that we have, is the total sample size for that group minus 1. But here we have two groups, so we'd subtract 1 degree of freedom for each, so that the total degrees of freedom are actually going to be 10 minus 2, or 8. So we'll take 5 minus 1 plus 5 minus 1 for degrees of freedom of 8. Then we would have to go to the tabled t-statistic with 8 degrees of freedom, looking at splitting a significance level of 0.05 into two tails, in other words, 0.025 in each of the tails, and we would see that the tabled value is 2.306. So the rejection region then is any value of the t-statistic that's 2.306 or something bigger, or negative 2.306 or something smaller. Where did ours fall? So we calculated a t of negative 1.34, which we would say falls in the fail to reject, or the acceptance region. So we'd say, is it likely that we would have observed this t-statistic just by chance alone if there was truly no difference? Yes, it's still likely. And in fact, that translates to the same thing as we saw. It translates into saying, is it likely that we would have observed this difference of negative 3.4 just by chance alone if the true difference was 0? Yes, it's likely. It's likely. So based on this, we'd fail to reject the null hypothesis, conclude that it's likely that we sampled from populations in which the difference in mean anxiety scores was 0. What does that translate to in English terms? Is there a difference or no difference between the drug and placebo group? No difference. No difference. So based on our data, there doesn't appear to be a difference. How would we calculate the p-value if we wanted to? Remember, the p-value says, look at the value of the test statistic that you observed in your data. We calculated negative 1.34. Calculate the probability of observing that value or something more extreme in either direction for a two-sided test. So again, we'd have to look at the t-table to get this, this probability, or we would have to rely on Stata or another statistical analysis package to calculate it for us. But the one-sided probability is about 11%. Two-sided would be 0.22 or 22%. Again, confirming that it's likely that we'd observe this difference in means just due to chance alone, even if there was no true difference in the mean anxiety score between the two groups. So those two ways were consistent, looking at whether or not our test statistic fell in the rejection region or not. It didn't. Our p-value is much bigger than 0.05. And remember, our statistical decision making was based on having a p-value less than 0.05 would cause us to reject the null hypothesis. And then what's the last way? Confidence interval. So it's not the last way, it's another way. And again, it provides us with more information than we get in just making this decision based on a hypothesis test. So you might be somewhat intimidated by this formula, but it's nothing more than a formula that takes the sample statistic, in other words, our observed difference of -3.4 in the mean difference in anxiety scores, plus or minus the table T that went along with 8 degrees of freedom and a two-sided alpha of 0.05, times the standard error that we get, which is a function of the sample standard deviations and a function of the two sample sizes. So we're just forming an interval around our observed difference, and we see that that interval ranges from -9.2 up to 2.4. And if we were interested in testing the null hypothesis of no difference, we'd inspect that interval to see if it included 0. Does it include 0? Yes. So again, based on this confidence interval, the interval says the difference between drug and placebo is that the drug could reduce mean anxiety as much as 9.2 points on average, or it could actually increase anxiety by as much as 2.4 points on average. But this is a pretty wide interval. It contains 0. There's no evidence based on our data for rejecting a hypothesis that they're the same. Okay, so we've just expanded then from going from a one-sample comparison to a two-group comparison. And I'd like to take you then to the different scenario in which we may think we have two groups, but the groups are actually not independent. They're correlated because they either are related in one way or another, either because it's a pre-post design, a before and after measurement, or the same measurement on the two measurements on the same set of individuals. So what we're going to see is that actually when we have two samples that are not independent, when they're related, we can actually think of this as a simple random sample from a population of differences of paired observations. So let's look at an example to make some sense of this. We'll be setting up then a test statistic for a hypothesis that the mean difference equals 0, and then we'll set up a 95% confidence interval for the true mean difference in paired observations. So again, this slide should look pretty familiar. It's all a variation on the same theme. Our test statistic is still going to be the sample statistic minus the hypothesized value over the standard error, and we'll need to know all three components in order to calculate this test statistic. So I'm going to use the same values that we used in the previous example, but now, in fact, we'll set up a scenario that these are 5 patients, not 10. In the previous example, we had 5 patients treated by drug and 5 separate patients treated by placebo. We have a patient who's treated the first week by drug. Then there's a washout period, and they're treated the second week by placebo, so that we could look at the difference between their measures from drug and placebo for each. So 19 minus 22 would give a difference of -3. 11 minus 18 is -7. So we could calculate 5 differences for these 5 individuals. Does that make sense? So now we only have a sample size of 5. It's a crossover placebo drug trial that's aimed at looking at whether the drug decreases anxiety, but we're basically using each person as their own control. So the fact that we're able to look back at these individuals, we see that actually, even if we look at the placebo measures, there's some variability in placebo, and those who tend to have low scores for placebo tend to have relatively low scores when they're treated by drug, whereas those who have high scores when they're treated by placebo tend to have relatively high scores. So in a paired design like this, where we're using each patient as their own control, we're able to account for individual variability and look at the within patient difference. So we can calculate the mean difference just by taking the average of those 5 differences as -3.4. We can calculate a standard deviation of the difference in the same way, just looking at the variability of each difference from the mean difference of -3.4. We'd see that that standard deviation is 2.1. And because of the algebraic truth that the difference between two means is the same as the mean difference, we would see that this mean difference in the paired relationship shows that the drug anxiety score was 3.4 points, 3.4 points lower, indicating a decrease in anxiety score with drug as compared to placebo. Okay, so the test statistic, again, is a variation on the same theme, but it's now our statistic of interest is the mean difference. And we're hypothesizing that the true mean difference is 0, so we'd subtract the value of 0, and then divide by the standard deviation or the standard error of the mean difference, which takes the standard deviation divided by the square root of the sample size. And that would calculate as negative 3.6. Now, does this look vaguely familiar? It should, because if I had substituted an x in here instead of a d, I'd have x bar and s for SD. So in fact, when you look at differences in paired comparisons, it just reduces basically to a one-sample t-test. It's just that now we're looking at calculating differences, and we have a sample of differences rather than a sample of observations. So that t-statistic is negative 3.6. Again, we'd like to make a statistical decision about whether or not the null hypothesis of mean difference equaling 0 by either inspecting the rejection region, setting up a p-value, calculating a 95% confidence interval. Okay, so where would we go from here? So the only difference is that now our sample size is looking at a sample of 5 individuals in which we're able to calculate differences for each of the 5. So the degrees of freedom are 5 minus 1, or 4. So again, we'd look up the tabled t-statistic with 4 degrees of freedom, significance level of 0.05, split in 2 tails, and we would see that that value is 2.776 and negative 2.776. So that our calculation, if you recall from the previous slide, was a t-statistic of negative 3.6. Where does negative 3.6 fall? In the rejection region or in the fail to reject? Falls far in the left tail of the rejection region, indicating that our observation, which was a difference of negative 3.4 points between drug and placebo, is something that's far different from what we would expect just due to chance alone if there was truly no difference between drug and placebo. So the values that we would have expected would have been ones close to 0, translating into a t-statistic close to 0. Ours is a very low negative number, negative 3.6, falling far out here in the rejection region. So we'd reject the null hypothesis, and we would conclude that, that based on our data, there does appear to be a significant effect of the drug in reducing anxiety score when we've used an experimental design in which each patient serves as their own control. So again, what we would want to do is look at the p-value. Again, from the table, we'd see the one-sided p-value is about 0.01. The two-sided is about 0.02, much less than 0.05. Again, the p-value would give us evidence for rejecting the null hypothesis. And what happens if we calculate a 95% confidence interval? We'd take the mean difference of negative 3.4, add and subtract the tabled t-statistic of 2.776 times the standard error, and we'd see that that value ranges from negative 6, that interval ranges from negative 6 to negative 0.8. Does it include the hypothesized value of 0? No. Getting close, but it doesn't. So based on this, again, it would agree with our conclusions based on looking at the rejection region or the p-value. Okay. So all that we've done is expand this. We've expanded the whole framework for setting up a hypothesis test or constructing a confidence interval to take us from two sample comparisons to study designs in which we actually have paired comparisons. Why don't I take you now to the same examples using Stata. And at this time, too, you can let me know if you have any questions about an interpretation. So we're just going to run through this again, but this time instead of calculating it by hand, see how we could interpret this based on a Stata output. So again, Stata doesn't need the whole data set, which actually comes in very convenient if you'd like to just verify something that you're reading in a journal article or some summary value. So here, remember what we had when we had the two independent groups. We had 5 observations that were treated by drug, and the mean anxiety score was 16.8, and the standard deviation was 4.6. Then we had the placebo group, 5 observations, with a mean of 20.2. and a standard deviation of 3.3. So now, and I'm going to take you then to looking just at what we have in the lower part. What Stata tells us is that this is a 2-sample t-test with equal variances. Now, what do we know about the variances in the population? Anything? Nothing. We actually know nothing about the population variances. We can look at the sample standard deviations. What we calculated based on these 2 samples of 5 was that the sample standard deviation was 4.6 in one group and 3.3 in another group. There are ways to test whether these are statistically significantly different, but I'm not going to show you that. Instead, I'm going to show you, if I assumed unequal variances, how we would interpret the test result, and we'll see if we get any differences in conclusion. So how would I read this output? I have the first group of 5 observations, its mean, its standard error, which takes the standard deviation divided by the square root of the sample size. And in fact, it also gives me a confidence interval. So if I look at the one group, this was the drug group, the 95% confidence interval for the anxiety score ranges from 11 to 22. Here's the second group that was treated by placebo. Its mean was 20.2. Standard error that we get by taking 3.3 divided by the square root of 5 is 1.4. And the 95% confidence interval was 16, ranging up to 24. So if I did nothing more than compare these 2 confidence intervals, what would you conclude regarding whether or not mean anxiety score is the same or different in the 2 groups? They're the same because they overlap. So based on this overlap, we'd conclude that they appear to be the same. The other way, though, that we looked at this was by looking at the difference. The difference in means was negative 3.4. The standard error that Stata calculated for us, remember the standard error depended on the sample variances, the sample sizes in both groups, but it would give us then a 95% confidence interval that ranged from negative 9 up to 2.4. Remember, this is what we calculated by hand, and it includes 0. So either by seeing that the 2 separate confidence intervals overlapped or that the confidence interval on the mean difference contains 0 gives us the same conclusion. Does this make sense? What else is Stata allowing us to do? One had equal variances, one had unequal variances. And so if I set up, and let's look at the bottom part, if I set up a null hypothesis that the difference in the true population means, and this is how Stata writes it as mean x minus mean y, but it is really mu1 minus mu2 equals 0 versus an alternative that it's not. Here we see the calculated t-statistic of negative 1.34 that we calculated by hand, and the corresponding p-value of 0.22. So based on that p-value, it's much bigger than 0.05. Again, we'd fail to reject the null hypothesis. We'd conclude that there doesn't appear to be any difference in mean anxiety score between these 2 groups. Okay? So most of the time, you won't be calculating these by hand. Most of the time, what you'll be doing is interpreting confidence intervals or the results of hypothesis tests, either in your reading of journal articles or in working with a group. Now, one of these assumed equal variances, one assumed unequal variances. What do we notice about the difference in the p-value? 0.2162 versus 0.2198. Does the conclusion change in this example? No. So our conclusion would remain the same for this particular example. Okay. Well, I'll move on to the single sample case unless there are any questions about this. Yes?
This study is inadequately powered, so statistical conclusions won't
Yeah, okay, so this was a good point. The question was that this study, this particular study may not be adequately powered to find a difference in mean anxiety score. This is an excellent point, and tomorrow we will spend most of the time talking about sample size and statistical power considerations. But it was a very good point. In this case, this was a simple example that we were using for illustration. It only had 5 individuals in each. So certainly the fact that we see a difference of negative 3.4, that may be meaningful. It may be meaningful to us, but the fact that our sample size is small influences our standard error, which influences 2 things. It influences the width of the confidence interval, and as well it influences the value of the test statistic. So if we had had a bigger sample size, suppose we had 50 in both groups, we indeed might have seen that the sample sizes would have resulted in smaller more narrow confidence intervals. We may have gotten a different value of the t-statistic because the standard error would change. But we'll explore this more in detail tomorrow. But very good point. Shall we look at the example then of if this was a paired design? So if it was a paired design, we would actually only have a single sample of 5 differences. So remember, we had our sample size of 5. The difference was negative 3.4. The standard deviation was 2.1. And suppose we set up a null hypothesis that the difference was equal to 0. This t-test of paired differences, as I said, reduces to a 1-sample t-test of the difference. 5 observations. Mean difference was negative 3.4. Standard deviation is 2.1, so 2.1 divided by the square root of 5 gives us the standard error. And we see here the confidence interval that ranges from negative 6 up to about negative 0.8, just like we derived by hand. It doesn't include 0, just barely doesn't include 0. And the t-test would give us a test statistic of negative 3.6, just like we derived by hand, with a p-value of 0.02. So again, the p-value would cause us to reject this null hypothesis that the mean difference equals 0, just as by inspecting the confidence interval, we see that it doesn't include 0. I've come to the end of this material, and so what I'm going to do is just summarize again what we did, and then I'll open this up for some discussion. We can go back and look at stata again, or we can go back and look at any of the other examples that we've covered up to this point. So what we've done over the past 35 or so minutes is we've looked at, again, using a knowledge of theoretical sampling distributions to set up hypothesis tests, to construct confidence intervals, either for 2 groups in which we have continuous data, so we're interested in looking at differences in means, or if we have 1 group in which we have paired observations, pre versus post, before versus after, and we're interested in mean differences between observations. Okay, so let me minimize that and see if there are any questions. Yes, here comes a microphone.
I had a question. You've shown that you can use the p-value or the confidence interval. Is there a reason to use one or the other in publishing data?
Right, so that's a very good question. The question was the use of the confidence interval versus the p-value. So I'll just point at the last one that we looked at, which gave us a confidence interval that ranged between negative 6 up to 0.8. So this actually gave us, based on our data, which only was 5 observations, gave us a range of possible values that were consistent with the truth. We see that it could be as low as negative 6. It could be as high as only less than a 1-point difference in mean anxiety score. So depending on the ramifications of the treatment, we might say, well, it's not worth investing in the new drug. It might not be worth the time, the money, the potential side effects if there's only the potential of possibly less than a 1-point difference in mean anxiety score. Now, what happens if we base all of our conclusions on the p-value? Remember, the p-value is based on a null hypothesis that the true mean difference is 0. It's a p-value that says only 2 out of 100 times would we expect to see the difference that we did, just due to chance alone. It is less than 0.05, but remember 0.05 is a guideline. If we had increased the sample size to 50, the confidence interval would have been narrower, the p-value would have been lower, and by basing a decision just on a p-value, it's very heavily influenced by the sample size, and it's also places our decision making in this black or white cut and dry mode, whereas the confidence interval gives us a range of values on which to base our decision making. Question in the back.
Does it matter whether you describe your data as the mean plus or minus the standard deviation or the standard error?
Great question. Question was, what is really the difference between standard deviation and standard error? And this is, if we wanted to say this is a way to lie with statistics, sometimes it can be. Let's look at again at this bottom panel. The standard deviation was 2.1, and that's an indication now of the variability of the differences that we observed in this sample. It's a measure of variability in the actual observations. The standard error, on the other hand, is the standard deviation divided by the square root of the sample size. So by definition, the standard error is always going to be smaller. So if I wanted to make it perfectly clear, I would certainly label my mean plus or minus the standard deviation or the standard error appropriately. So often what we see for as SD represents standard deviation, it's the calculated sample standard deviation, whereas SE for standard error is used. For someone who's typically reading a journal article, you might tune in more to the fact that it's a standard deviation or expect it to be a standard deviation, so that if the writer of an article chose to present standard errors and the reader misinterpreted it as a standard deviation, then it would look like there's far more precision associated with the estimate than there might really be. So in other words, you can express both. Typically, the standard deviation is shown. It might say mean and standard deviation, and so the reader is expecting to look at an estimate of the variability in the observations. The standard error can artificially look like there's little variability if it's not advertised as the standard error or made clear that it's the standard error. Does that help answer your question?
Practical question.
Yes.
How much does the site license for intercooled Stata 7.0
Practical
cost?
question, yeah. You know, this is a good thing. I'm not a proponent of, I don't have stock in Stata, but if you go to the website of www.stata.com, it gives all of the prices, and it depends on whether you can get an educational license or a single user or a site license. I would encourage all of you who are associated with VAs that have institutional or university ties to explore whether Stata might be available already at universities that you're affiliated with. It's very inexpensive for educational purposes.
Sort of as a follow-up to the question on standard error versus standard deviation, what, in reporting it, is there anything that seems more appealing to a purist?
To a purist, because of the fact that often standard deviations are given to represent the variability in a set of observations, which is, again, remember, estimating the variability in the true underlying population. So SD, or the standard deviation, or S, the sample standard deviation, is just an estimate of the population sigma, the population standard deviation. So most of the time, readers may be tuned in to the fact that it's a standard deviation representing variability. The standard error represents what type of variability in the sample statistic. So the standard error is really representing the variability in all the possible mean differences that exist, because it's divided by the square root of the sample size. So imagine that the sample size was 50 instead of 5. The standard error would be very, very small. And if it was 500, the standard error would be even smaller. So if the uneducated reader was misinterpreting the standard error as the standard deviation, the uneducated reader would think that there's really not very much variability associated with this measurement at all. So either can be used. I would just suggest that you make it very clear that one is the standard deviation and one is the standard error. And question, yourself when you're reading an article whether the standard deviation or the standard error is presented.
Can you go over that shortcut static commands that you used?
Sure, I can. The static command, just to show you briefly, was that what I put in for the paired comparison, which boiled down to a single sample comparison, was Stata has a t-test I command, and the I means immediate. So you don't need an open data set. You don't need a data set. You just need summary statistics. There is a help command in Stata. So if I forgot how to do this, I could look at the help command, and I would find out that for a single value, I just need to put in the number of observations, in other words, the sample size, the mean value, the standard deviation, and the hypothesized value. So just to reiterate this last panel, I looked at the t-test where my sample size was 5, the mean difference was negative 3.4 in my sample, the standard deviation was 2.1, and then the hypothesized value was that the mean difference was equal to 0. And so it's that command that I put in: number of observations, observed mean difference in the sample, observed sample standard deviation, and a hypothesized value of 0 that allowed me to replicate what we did by hand.
A t-test is relatively easy to use. And in many clinical studies, you will have, say, 2 populations, but multiple interventions or multiple data sets. And if you do enough t-tests, eventually something comes up positive.
Right.
Is there a way to modify the t-test, or a way that's accepted to modify the t-test so you can use a t-test multiple times as opposed to having to use an analysis of variance?
Yes. So this is a question which really is the multiple comparisons problem, where if you look enough times, you're bound to get a statistically significant difference just by chance alone. And so the more you look, the more you will find. The more comparisons you do, the more that will be significant. So we will talk about this in the context of comparing more than 2 groups when we deal with analysis of variance tomorrow. But the ways that there are a number of different ways. Most of them deal with modifying the significance level. So we've been choosing a significance level in alpha of 0.05. Often, if a priori you know that you're going to make 20 different comparisons, to be conservative, one could divide 0.05 by 20, or some other technique that would modify the significance level. They all tend to reduce the rejection of the null hypothesis. So if you reduce the significance level, you're less likely to reject the null hypothesis, which means you're less likely to find statistically significant differences. So it's an excellent question, because we can find significant differences just by looking and looking and looking. We can find statistically significant differences by inflating our sample size. And we have to keep in mind that statistics is a tool, and that although there are methods for trying to make the best possible decisions and to aim tools that help us try to modify our decision making when we're making multiple comparisons or comparing many groups, it's still just a tool. So so this whole area of multiple comparisons is one. The other is that all the techniques that we've been reviewing up to this point in time are ones that we would call classical statistical inference, that's based on p-values, the use of p-values. There's another area of statistical inference that doesn't use p-values at all. It's using likelihood and relative comparisons of likelihood as opposed to p-values. So there are multiple ways in which one could try to account for the question that you asked.
You triggered a very interesting point in my mind. There's an old saying that the closer you can remain to the raw data in your descriptive statistics, the better you are with respect to representing reality. Can you respond to that?
Yeah. So the comment was that the closer you remain to your raw data, the better off you are. And certainly, you don't want your statistics to tell you something different than what your data tell you. So we started out this course by saying, look at your data, examine the distribution, see what relationships hold. And so although there can be very complicated statistical analyses that are performed to adjust for differences in covariates and confounding, what you would like to be able to do is really say, these are my data, these are how they look in tables, these are some descriptive statistics. If I account for certain relationships, I can also interpret them with statistical inferential techniques, testing or modeling. But you would like to be able to say that the data support your conclusion, and that looking at the raw data should give you an idea of what sort of conclusion you might get. You might need to adjust your conclusion a bit based on relationships that you don't, that you're not able to account for by just looking at a 2-by-2 table or a difference in means. But I certainly agree with your statement. You don't want to distort the data with your statistical methods. Yep.
Back to the standard error versus standard deviation issue. A sample statistic is basically, in my mind, always what you're going to be interested in reporting. You're going to report means of whatever, continuous variable, for instance, you we're studying. And since that's a sample statistic, then I would think that standard error would always be the appropriate choice. Is that
so,
how do you
so
respond
actually,
to that?
think of what, when we've set up a normal probability distribution to describe continuous measures, we've assumed that we're sampling from a population where the parameters of interest are the mean and the standard deviation, so mu and sigma. When we take a sample, which is what we do when we perform a study, we are able to estimate that mean mu by the sample statistic, x bar, the sample mean. We're able to estimate the variability in the population based on the sample by using S, the sample standard deviation. So if we wanted to describe the spread in the population based on our best estimate, the one we get from the sample, we would choose to use the standard deviation S as this measure of spread. The standard error is, as I said, is based on the standard deviation as well as the sample size. So it's going to be determined by the sample size. We could have the same spread of 2.1 in a sample of 5 and a sample of 50, but the standard error is going to be quite different depending on whether the sample size is 5 or 50. And so that's the concern, that if the eye, as a reader, misinterprets a standard error in a table as a standard deviation, one would have thought that there was much less variability than in the population than there really was, because that standard error is always going to be much less than the standard deviation. So am I advocating never reporting standard errors? No. I'm just advocating that if you report a standard error, that you should very clearly define it as being a standard error. And this one is the standard error of the mean. It's not the standard deviation of the sample, it's the standard error of the mean, whereas S, the standard deviation, is the standard deviation indicating variability in the sample. Just two different measures. Okay. One last question? We've had a lot of good questions. Okay. The last word.
Well, I guess I've asked you this question before on the side, but that was on the first day, the first talk.
Okay.
That was about the way p-values are talked about in the literature. You know, if the p-value is really low, then the investigator will go on to say that based on the p-value, that it was highly significant.
Right.
Or if the p-value is 0.06, they will say it showed a trend towards significance.
Right. So you know, this issue of reporting p-values, where p less than 0.05 is considered statistically significant. Some will say a p less than 0.01 is highly statistically significant. A p less than 0.001 is very highly statistically significant. So we would keep adding, you know, adjectives to this. Let me just show you what happens if I change this to a sample size of 50. Look what happened. We went from observations, sample size of 5 with a p-value of 0.02. We changed the sample size to 50, and it was 0.0000. So we still had the same difference in mean. We still had the same standard deviation. It's just that the sample size had increased to 50, which decreased our standard error, which said it's really unlikely that we would see a difference of negative 3.4 if the truth was 0. But if I change the sample size to, say, 25, so 25 or 50 both gave a p-value of 0.0000 that we would say is highly statistically significant. Now, let's look at this one with 25. The mean, so it's saying on average, the mean anxiety score has decreased with drug by about 3 points. The 95% confidence interval says it's somewhere between -4 and -2.5 point drop. So the p-value says this is very highly unlikely that we would see this difference just due to chance alone. But what's the meaning of a 2 to 4 point difference in the mean anxiety score? It really depends on the scale, depends on the instrument, it depends on what is a meaningful difference in terms of quality of life and functioning. We could have a very highly statistically significant result based on the p-value, incredibly highly statistically significant because it's almost 0, but in fact the 95% confidence interval might give us some more information, might help us interpret whether or not we'd really want to put this drug into place. So I hope that sort of answered your question.
I always feel uncomfortable when I see that written in the articles. I'd be more comfortable if they said, you know, p-value was this and it was significant, and not add any adjective to it.
Right,
you know.
right. No, and actually there's been a trend. Many journals don't even accept p-values anymore. You know, they'd prefer to see the 95% confidence intervals or request both the p-value and the 95% confidence interval. So I'm with you. I wouldn't like to go with those adjectives either. I'd prefer to see the 95% confidence interval, get a little bit more information. If the conclusion also has a p-value quoted with it, that's fine, but in my decision making, I'd prefer to have the confidence interval. Okay.